is coming or only the screen is coming and sound is coming, and when we'll stop this, your board and you'll come through the camera.
प्रॉब्लम तो नहीं आएगी?
नहीं आएगी सर. हाँ.
अच्छा. कहाँ गया वो ड्राइव? किस में ओपन था? नहीं नहीं, इट्स ओपन. ठीक है. ओहो. अच्छा, इट विल बी इन योर मेल ऑल्सो ना? मैंने जो कल मेल भेजी है. सॉरी, तो मैं मेल खोल रहा हूँ मैं पब्लिकली. मेरी मेल एक आई होगी ना इसमें. Okay, so we are officially starting now because the recording has come. I didn't want it to skip the recording. So, how to increase the font of this? Control plus. Okay. So I think I just wanted to go over the drive once so that I'll go over the feedback. Most of you, I think 80% of you think pace is fine. Something it's fast for those you have to stop me as we go along. Something it's slow. So for those, I would say bring your research paper and try to match with the class. Take a printout of it and use it in the classes. Material and lectures are good. Then you want more practical problems. So now for that, what I'm doing is starting today in the lab, I'll cover 3 to 5 papers from each projects and go over and highlight the components of the class. Now that you know a little bit about Lagrange multipliers, LP also you would know. So this will make it easier. Then practice problem, this is on the drive, which I'll go over in a minute. There were few other suggestions that give tutorial for homework. I think you should do this by yourself. I'm now uploading tutorial well in advance. Feel sleepy after lunch. I can't do much. Better jokes. Break the long proofs into small. This was one comment by one person, but I'm trying to break it into smaller parts anyways. Then cover all the basic concept. This was also one person has just mentioned, but I'm trying to cover as many basics as I could, and I'm uploading the supporting material. So you have to read the supporting material before you come to the class. But I'll be try to be more explicit and ask more questions. This, of course, so these 5 are small things, but more important was the practical problems, which are we are doing it in the lab. I'm going to do and practice problems. So now let's go to drive. In case you have not been looking to the drive, I'll just highlight it once. It's sorted wrongly. Okay, so lectures you saw 1, 2, 3, 4, 5, 6, 7, 8, which is today's lecture is already there. So it's there for you. What and tutorials? This tutorial is also there. This would be done today, I think. Tomorrow, sorry. What I wanted to highlight, lab. Okay, today in the lab, what we'll do, we'll start simplex, because we'll start simplex today. That is there. Those who want to take a look offline, I wanted to highlight recordings. I'm sure you're going to take a look at it. Supporting material, there'll be some simplex theory which I'm going to refer to. So this is there, the 3 questions. This will make sense once I start teaching today. So go back and take a look. I don't want to turn the projector on again. So that's why I'm talking about it. But based on your feedback, these are 4 questions on classification and necessary conditions. This you can go, and after today's class, there are 8 questions on this. Except the last question, you can go over and practice all the other problems. All these are doable. Except first 5 problems you can do. I think we'll see how much it goes. So they are practice problems here. So that is what I wanted to highlight. So now coming to the lecture which we want to start. This is what I was revising you just when the recording was not working. So I'm going to just bring this on the screen once. Okay, so when you have inequality constraints, this is what I was saying. The second order necessary is that if it is a constrained local minimizer and a regular point, then these five are the KKT conditions, and Hessian of the Lagrangian is positive definite over null space of Jacobian of constraints that are active at x star. So this is different with the equality constraint condition because there all constraints were active. Here now some will be active, some will not be active. So the Jacobian matrix will not just carry all the active constraints, but all the equality constraint, but the active inequality constraint as well. So it will be slightly bigger. So that is what I mentioned. Once you do more problems, this will be clearer. The sufficiency condition is same. If these things are true, then it is a strong local minimizer, and this last condition is same, that Hessian is positive definite over null space of Jacobian of constraints that are active at x star. So that's the only difference when you go from equality to inequality, besides the fact that two conditions become five in the necessary case. The sufficiency conditions, there was no active adjective there, there is an active adjective here. Everybody okay? All right. So we're going to stop this and start the board. Can you turn it off now and switch that? So we'll start linear programming. Did any of you was able to figure out what's the simplified expression? It is C is equal to A transpose lambda plus B. That is what you should get. So in case you didn't get it, we'll work it out now. Okay, so we are starting part 4, which is LP and QP. We'll do both of them here. That's what we're doing. And so when we're doing intro of the LP problem, so I think if you look at the papers which you guys have selected for the project, about if not half, a third of you have taken linear programming. So linear programs are very popular, whether it's finance problems, or you can look at operations research problem, or you can even take physics problem. They arise at a lot of places. The good part about the linear program, which now I'm going to highlight later on, is that the feasible region of a linear program forms a feasible polytope, which means that in a two-dimensional space it will be a polygon. In a three-dimensional space it is called, we'll come to that, so polyhedron and so on and so forth. The feasible region is defined by this for a linear program. This is what I've uploaded on the drive, the proof of that. So you can do, that's the first question. Second observation for a linear program theoretically is that the solution of a linear program lies on the vertices of this polygon. This also you can prove. First, the feasible region is formed of in a two-dimensional space, a polygon. The second observation or the proof is that the solution lies on the vertices of that. So now your work becomes easier. That if you have to develop an algorithm around it, you first figure out the polygon, go to a vertex and iterate. And where you get the minimum value, you can stop. So exhaustively you will check all the vertices. So can you do better than that? So we'll see about that. So this is the feasible region. So solution on vertex. And then you iterate. Iterate on vertices to get the solution. Okay. So that's one thing about the linear program. Another observation, standard form, I think somebody said I didn't come to class. So linear program is the simplest you can remember as standard form subject to ax equal to b, x greater than equal to 0. You can write this that x is belonging to an n-dimensional space and your A is r cross n, which implies b is also n. And usually, typically, r is less than n because you want the problem to be underdetermined. Correct. What's your name? Huh? Vashit. Okay, Vashit. So somebody remember. So underdetermined because the constraints will give you infinite solution, and you have to find one solution which minimizes your objective function. So that is why it is there. Huh? Then you, like we did in the classification when we talked about constraint optimization, another form of this is minimize C transpose X subject to Ax greater than equal to B. So how did we convert this form into the standard form? You did with me and then you did a whole tutorial. Jago. Huh. Introduce a new variable. First of all, ax minus b is equal to y. So y will be greater than equal to 0. But the standard form requires the non-negativity on all the variables. So what did we do? Correct. So I'm not working it out because you've seen it, I'm just revising it. X is equal to x plus minus x minus. So now your x hat is x plus, x minus and y, and all of them are greater than equal to 0. This is one thing. Your constraints will now become a minus a identity, x plus x minus y is equal to b. Correct? That I'm going reverse order. This is the inequality constraint, this is the equality constraint, and now the objective function is C transpose minus C transpose 0, x plus x minus y. Everybody comfortable? You've done many problems in this. Another observation which we did earlier was its relation to CP. So we said that the linear program is a convex program because what is the objective function? C transpose X is linear. What's the Hessian for this? Zero matrix, which implies it's positive, semi-positive, semi-definite, sorry. Positive, semi-definite. What about the equality constraint? Again linear, same thing, so they are convex. It's convex and concave both. Inequality constraints, again linear, so same thing except that we are considering this as concave rather than convex. Everybody recalled all of LP? It was just a revision of what you've seen. Now we'll do what I was making you do in the free time. So we'll now very quickly jump to the necessary and sufficient conditions which you have spent so much time with. So this says so we formally write it down. So if it's a theorem, if x star is a regular point of constraints active at x star, then it is a global, see the wordings, it's global solution of, this is the problem. I'll write this really big. If and only if. So the A constraint is that it should be a feasible solution. B was X should be the feasibility for the inequality constraint. The C condition is C A transpose lambda plus mu. E condition is mu I xi greater than equal to 0, I going from 1 through n, and sorry D, and E was x is mu is greater than equal to 0. I mean, I'm referring to this I, you can refer to this as J because we are talking about inequality constraints. Okay. First, let's look at the predicate of the theorem. It says that if it's a regular point, if x star is a regular point of your standard linear program, and it's a regular point for the constraints that are active at x star. Why are we referring to it active now? Because we have both equality and inequality, right? So you should remember that this is the standard form, those who forget, but I think I'll write it down on the side. Ax equal to b and x greater than equal to 0. So there is equality and there is inequality. So in the inequality, some would be active at x star, some would be inactive. So you have to check the regularity for all of them, all equality and the active inequality. Then it says, then it is a global solution of 1. It makes things very easy for you. Why we are referring to this as a global solution? Because it's a convex problem. So whatever solution I will find will be global. So it's global. The second thing it says is if and only if. How does the necessary condition go? If this is a minimizer, then all this should be true. Second order, maybe it goes the forward direction, second order necessary. If it is a minimizer, this will be true, and there was an F condition. Remember? Hessian of the Lagrangian is positive, semi-definite over null space of Jacobian constraint. Then when we went to the sufficiency, we went the other direction. If this is true, then it is a strong local minimizer. Now it is saying it's if and only if condition, which means that this is necessary and sufficient both. If it is a minimizer, then these are true. If these are true, then it is a minimizer. And the good part is that the F condition is not playing any role here. It turns out that the Hessian of the Lagrangian will turn out to be positive semi-definite or positive definite over all of the space, and you would not have to worry about it. Everybody okay? All right. So now what I was making you do in the free time, these are just the 5 KKT condition for the first order necessary, which you have seen with the inequality constraint. You have a question? Sorry. Ax equal to b. Sorry? Jaldi mein likh raha hu. I thought we lost so much time in this recording business. Which comes slightly earlier. I know it's not your fault, and I am doing this recording for maybe not for you, for those who don't come to the class. I'm being extra nice that ghar baith ke padh lo. But I wanted to record, so that's why we spent so much time. So these were the 5 KKT condition. This is straightforward: feasibility equality, feasibility inequality, straightforward complementarity, straightforward non-negativity. What I wanted you was take the general form and transform this into for the linear program, how this came. This is what. So those who were able to do, that's okay. For those who have not done it, we'll work this part out now. Is that okay? So what was the original condition? Gradient of the function is linear combination of gradient of constraints. J going from 1 through R, I going from 1 through, what did we use? R and S. This is what we were using. Here S is equal to N because they are N inequality constraints. Everybody okay? So now we'll do one by one. So we'll first take gradient of the function. So gradient of the function is gradient of C transpose X. This by now you should answer me like 2 plus 2 is equal to 4. So this is gradient of C1. You can write all of them till Cn, x1 to xn, gradient of C1 x1 till Cn xn. Take partial with respect to x1, it will be C1, with respect to x2, it will be C2. This now you should remember. I don't want any one of you to even think about this. It's so straightforward. Yes? So this is nothing fancy here. We'll look at the other two. So let's look at the second one. So the second term is summation of j going from 1 through s mu j gradient of cj x. Correct? So summation j going from 1 through n mu j gradient of what is cj? It's just x, you know. You can say xj if you want to say. So now what will this be? It will be mu1, or you can pull this inside. J is equal to 1 through n gradient of mu j xj. Correct? So we can also write this as mu1 mu2 mu n x1 x2 xn. Anything wrong with this? Yes or no? So this can also be written as gradient of mu transpose x, which is, like we did C, it is mu. Everybody with me? Now we do the other term. So we did this term, we did this term. We wanted to show that C is equal to A transpose lambda plus mu. This is the C which we are trying to work it out. So we'll now look at the middle term. The middle term is summation of I going from 1 through R lambda I gradient of AI of X. Correct? So we'll do the same thing here. So we'll say summation. So we'll first see what is my AIs. So if it is AX equal to B, I can write A as A1 transpose till AR transpose, where A1 through AR are column vectors. Since I've put them in a row format, so I'm putting it a transpose on it. This multiplied with X is equal to B, which implies the constraints are A1 transpose X minus B1 all the way till AR transpose X minus BR. Correct? So we'll write it here. So this is summation of I is equal to 1 through R. I'll pull the lambda inside. So this is lambda I AI X AI transpose minus BI, the summation of that. Correct? So this can be written as gradient of lambda 1 A1 transpose X minus B1 plus lambda R transpose AR transpose X minus BR. Everybody with me? So I can write this as gradient of lambda 1 through lambda R times A1 transpose X minus B1 till AR transpose X minus BR. Same thing, just a product. This times this times this, till this times this. What will this mean? This is gradient of lambda transpose AX minus B. This also by now you should remember. I'm just showing it again because I saw so many of you lost. Making sense? अभी आ रहा है समझ? That very little dependency on previous class है ना? So what I'll do, I'll write this as lambda transpose AX minus lambda transpose B. This is gradient. This is a vector. What's the dimension of this vector? One cross R. Everybody agrees? Sorry. Lambda was R cross 1. कुछ गड़बड़ हो रहा है क्या? हाँ, A is R cross N. ठीक है. So it's 1 cross N. Before I write lambda transpose is 1 cross R and this is R cross N. So the whole thing is 1 cross N. That is why it's multiplying with X, which is N cross 1. And the whole thing is becoming scalar. So what we'll do is, so I will write this as gradient of A transpose lambda whole transpose X minus lambda transpose B. Now this is nothing but like your C transpose, है ना? We take the gradient of this, it will nothing be A transpose lambda. हो गया? Clear हो गया था तुम लोग को? Everybody at the back, straightforward. Now this small play around you should do when we do quadratic program. Again we'll take this condition and apply the quadratic here, quadratic here, quadratic here. Does anybody remember what is the standard form of a quadratic program? Half of X transpose HX plus C transpose X, whatever A transpose X plus B, that was the objective function. So you'll take the gradient of that will become HX minus B or whatever. Then the constraints we said were linear, AX equal to B, so the same thing will happen. The inequality constraints, were they there in the standard form? They were not there in what the QP it can actually have, but the standard form didn't have it. So you may want to simplify this again. Everybody okay? So we did this, which is C trans C, this is A transpose lambda, this is mu, so we showed all of you. So what we'll do, we'll now do a problem on this, and then we'll start deriving simplex. We'll take a break and derive simplex after that. Now you will appreciate why did we spend so much time studying the necessary and sufficient condition. In the unconstrained case, did you use the necessary and sufficient conditions to derive any of your algorithms? With Neminath, what you did? You didn't? What was steepest descent? Negative of the gradient is the maximum descent direction. When we went to the Newton's case, there we were actually using little bit of necessary conditions in deriving the Newton's direction, but I don't know whether he covered on that. But there is a intuition when you derive an algorithm. So here when we derive simplex, we'll be very religiously sticking to these 5 conditions. So we'll see that we start at a point where all 5 will not be satisfied, then we'll iterate and we'll see where all 5 will get satisfied. But we'll have to be smart about it, that if we are at a vertex of the feasible region, like I said at the very start, we go from one vertex to the next. It should not be that we go from a vertex and we go inside the feasible region, then we figure out how to come back to the boundary again. So all that we'll have to do. Those who are doing linear programs in their projects, I told you that I'm going to do simplex in the class and you can apply it, where the solution is always iterated on the boundary of the feasible region or the vertices of this polytope which I'm trying to do. There is a complementary technique to that, which is the interior point method, which I told to many of you. The interior point method, what it does, it starts inside the feasible region, it keeps iterating, keep finding a solution, and upon convergence it reaches the boundary, because we know that the solution lies on the boundary. So you should study the interior point methods on your own, those who are doing a LP related project. Is that okay? Alright. So we'll do a problem. Okay. So you saw the intro, you saw the necessary and sufficient, which is just the 5 KKT condition without the 6th condition, and it's a if and only if condition. It gives a global minima. We'll derive one analytical example, then we'll derive the whole thing. So the question is minimize x1 plus 4x2 subject to x1 plus x2 is equal to 1, and of course both the x's are non-negative, so it's giving you it in the standard form. Let's first write the C. What is the C vector? What is the A vector? What is B? What is C here? 1, 4 coming from here. What is A? 1, 1. There is only one constraint, so it's 1 cross 2 matrix, and B is just 1. Okay. Now we'll apply the necessary and sufficient conditions, but this is so simple to do that you can actually graphically find a solution for this. To find graphical solution, what will you do? First we'll plot the feasible region. What's the feasible region? This quadrant and this line, because put x1 0 you get x2 1, put x2 0 get x1 1, so it is passing through 1 0 comma 1 and 1 comma 0. So that you've defined. Now you have to look at the objective function. The objective function is x1 plus 4x2 is equal to d. So if you have to write it in the standard form, y is equal to mx plus c, this will mean x2 is equal to minus 1 over 4 x1 plus d over 4. What's the slope? It's minus 1 over 4, which means that it will be slightly on the other side. This is a positive slope, this is a negative slope. It's minus 1 over 4, so it will be like a slanted line. These will be the contours, which we call. Contours are where the objective function value is the same. Which side will the objective function value increase and which side will it decrease? If you put this guy to be 0 and this guy to be 1, then the d value is 4. And if you put the other direction, put this to be 0 and this to be 1, which means that this direction is the d value increasing. Correct? So you have to go the lower direction. So the point where this will intersect this will give you the minimum value. This is how we look at it graphically, although practically we never do it because we don't work in 2 dimensions. Everybody okay? So this is the global minimizer. But now we'll apply our necessary and sufficient conditions. So this was graphically. Now we'll apply the conditions. To apply the conditions, what do we do? Which you have done it with me. We'll apply the 5 conditions, right? Ax equal to b, which is x1 plus x2 is equal to 1. B was x is greater than equal to 0. C condition was that so what is, so this is by the way C transpose. So C is 1 comma 4 is equal to A transpose lambda plus mu1 mu2. We only have one lambda because we have one equality constraint. We have mu1 mu2 because we have two inequality constraints, x1 greater than 0, x2 greater than 0. Then the D condition is mu1 x1 is equal to 0, mu2 x2 is equal to 0, and E condition is mu1 greater than equal to 0, mu2 greater than equal to 0. How did we solve it? How did we solve it in the general case? Cases, right? So both are, let's say, well, you can do anyways, both are inactive because that's the easiest one to do. If both are inactive, meaning x1 is greater than 0, x2 is greater than 0, which is implied that mu1 is equal to 0, mu2 is equal to 0 from D. This also satisfies E, which is the mu's are greater than equal to 0. Now what do we put? Look at it. Yes, what's your name? Huh? Aditya. So Aditya, what should we do next? So A, B and C we can, but A, B we can't because we don't know x's. B anyway, so if you put it in the C condition, mu1 and mu2 equal to 0, what do you get? Lambda equal to 1 and lambda equal to 4. Is it possible? No. So when you put it in the C condition, so you get lambda equal to 1, lambda equal to 4. So this case is not possible. Okay. Now let's do the case which actually works. Then you can do the other cases. Only x active will not work. Only x2 active will work. Okay. So only x2 is active. Or you can say x1 is inactive, whichever way you are looking at it. So x1 is inactive. So mu1 is equal to 0 and x2 is equal to 0. So mu2 could be anything. Okay? So we have in one way we have satisfied the D condition, which is our starting point. E condition I'm not sure because I've still not know about mu2. So I can't say whether I've satisfied the E condition. So now we'll fall back on C, B and A and write it down, or C and A rather. So we'll write the C condition. So this is 1, 4 is equal to 1, 1 lambda plus 0 mu2. Right, so from this you get lambda is equal to 1, mu2 is equal to 3. Okay, and so this is coming from the C condition, so that is done. We look at the A condition. So this is actually greater than 0, so this is satisfying the E condition as well. So we go back to the A condition. X1 is 0, x2 is 0, so x1 is 1, x2 is equal to 0, so this is satisfying the B conditions as well. Correct? So what do we also have to check? Regularized, yeah. So what will be the Jacobian now? Jacobian of constraints would be which constraint is first? We have to put the equality constraint, right? The equality constraint is x1 plus x2 is equal to 1. The gradient of that would be 1, 1. So I'll put that in a row format. And then out of the two inequality constraint, one is active. X2 is active. So X2 is equal to 0. So when you differentiate this, 0 and 1. Correct? You're finding the gradient of the constraint X2. So is this full rank? Yes, it's already in the upper echelon form. You can't make it more than that. The rank of this is 2. The number of rows is 2. So it's a full row rank, or these two are linearly independent. Or you can write, or this is full row rank. So hence a regular point. Okay, do the other two cases by yourself and tell me where they are failing. So case 3 is x1 is active and x2 is inactive. So in this one, what's in the first case, what's the minimizer? Minimizer is 1, 0, and this is the global minimizer. You don't have to do anything. Forget about strong, local, weak, or whatever. It's global. Tell me why this is failing, so that I can see that you guys are getting some work. In front of Aditya, what's your name? Full names, please. Aditya what? Masood. Difficult. Who you are? From where are you guys? Okay, that's easier. So one is Haryana Aditya and Maharashtrian Aditya. Okay. I'm trying to remember more names. Tell me why this fails. And then case 4. Both are. What case we did? Both are active. Is it? One of the news will be negative. Can everybody try it? Why this is failing? Besides Athar. Why will this fail? This is very straightforward. Both are active. This will fail because the equality constraint itself is not satisfied. No? So x1 plus x2 is not equal to 1. So it's not a feasible point. So that's why it will not work. This one you had to work it out. So here the mu one will turn out to be -3. -3. Lambda would be 4 and this will fail. Everybody comfortable by now? Okay. So you want to take a break or should I keep going? Break. Okay. So take a break and come back and stop the recording.